So this is question 4 from chapter 6-1, sapling learning problem set. And so in this case we are given a couple of reactions and told what the concentration-based equilibrium constant is, and then we're asked to calculate the value of the equilibrium constant for this bottom reaction D in equilibrium with A plus 2B. So what we try and do is take the two equations that we know and combine them in some way to determine the equation that we do not know, the chemical reaction that we do not know. So the way I usually start working these problems is I begin with the equation right here, and I start with the first reactant that I come to. And so I need 1 mole of D. So I'm going to go up here and I'm going to look in these reactions, and I'm going to find the reaction, a reaction that has 1 mole of D as a reactant. If I don't see that, I might have to flip a reaction around or multiply through by some coefficient in order to get the number of moles and the species on the right side of the reaction. So for this first case, I'm looking for D. 1 mole of D as a reactant. I see this bottom reaction has 1 mole of D as a product, so I'm just going to reverse that. So I have D in equilibrium with 2 moles of C. So now over here I'm going to write a column for the equilibrium constants, Kc, and the Kc value for this reaction, now that I've flipped it, remember when I reverse a reaction I take 1 over the inverse of the equilibrium constant. So that's going to be 1 over 0.170. Okay, so that's that reaction, and there's the equilibrium constant. Now then I come to the equilibrium arrow in my reaction arrow. Okay, so now I'm looking for 1 mole of A as a product. So up here I have 1 mole of A, but it's a reactant, not a product, so I just have to flip that reaction around. So I've got 2C in equilibrium with 1 mole of A plus 2 moles of B. And again, since I've flipped that reaction, I'm going to need the inverse of the equilibrium constant. So the inverse of 2.99, like that. Now what I'm going to do is combine these two reactions. So I guess the next thing that I would do is just check that I have 2 moles of B as a product. And I have that already in this second reaction that I've written down, 2 moles of B as a product. So I'm ready to combine these reactions. So I'm just going to add them, combining everything that's a reactant on the reactant side of the equilibrium arrows and everything that's a product on the product side of the equilibrium arrows. So I've got D plus 2C for all my reactants. Then on the product side I've got 2C plus A plus 2B. And now if you look, we've got 2C on the reactant side and 2C on the product side. So what I can do is combine those and subtract 2C from both sides of this reaction, just as though it were an algebra problem, and they will cancel out. So what I'm left with is D in equilibrium with 1 mole of A plus 2 moles of B, and that's the reaction that I was looking for. So I've added these two reactions, so the question is, what is the equilibrium constant going to be? You might think we just add these two equilibrium constants, but we don't. We multiply them. So the equilibrium constant for this reaction that I want is going to be these first two equilibrium constants, one for each reaction, just multiplied together. So 1 over 0.170 times 1 over 2.99. And that should lead me to my answer. So remember, when we combine equations, we multiply equilibrium constants. Anytime we flip a reaction around, we take the inverse of the equilibrium constant. And I didn't have to do it in this case, but if I were to multiply a reaction through by some number to change the way that I balance it, so let's say I multiply through by 1/2, and I would end up with 1/2 A plus B in equilibrium with C, 1 mole of C. And so what would the equilibrium constant be here? Well, the equilibrium constant for this reaction is 2.99. So the equilibrium constant for this reaction is 2.99 raised to the 1/2 power. So I just raise it to the power of the number that I multiplied through by. So I multiplied through by 1/2, and that becomes the power that I would raise this to. So 2.99 to the 1/2 power.